All right, so welcome everybody. This is the second talk of this session, and I believe this is part one of a two-part series. Our speaker is Luís Bettencourt from the University of Chicago, the Santa Fe Institute, and the Complexity Science Hub in Vienna, Austria. And the talk is going to be about Towards the Statistical Mechanics of Cities, part one. Welcome, Luís, and thank you everybody for joining us.
Thank you very much, Maria. So let me just share my screen as usual. Just a second. Bring this up. Okay. And so I hope you can see it. Okay, good. Just minimize a few things. Great. So please, if you cannot hear me or cannot see the slides, interrupt me, but otherwise I'll assume that you can do it. So let me start with a couple of things before I get into the material. So first of all, thank you to Yuri and Oksana for organizing this. It's a great pleasure and an honor to be talking to you today and celebrating the spirit of Ising. I want to start by saluting all of you in Ukraine for your courage, your resilience, and your spirit of innovation. You've been showing everybody in the world what it takes to live with dignity and freedom. And so thank you for what you're going through. And I hope that soon we can do this, as was said, in person in a time of peace. So today I'll be talking about, as you can see from my title, the statistical mechanics of cities. So this may seem something a little bit reckless, given that statistical mechanics is in some sense not, it's been about physical systems, not about social systems, let alone something as complex as cities. But in some sense, you will also see that this is part of a bigger story, a story in which statistical mechanics in many ways has started and is now, after a century of studies of physics, going towards the direction essentially of information and computation, which are things that were not there to begin with. We used to do statistical mechanics of systems in equilibrium at maximum entropy. And so this tendency is something that requires models and examples. And it's in that spirit also that the work of Ising will give us a bridge to go through what I want to present to you today. So let me start by saying, connecting a little bit to Reinhardt's talk and using this photograph, which is in your paper with Yuri and so on. First, it's sort of a before and after, as you've seen before, and just echoes what we were discussing of the early lives of Ernst and Johanna in Germany. It was a life that, though troubled by the times, must also have been incredibly exciting, right? So at the forefront of physics in some of the best institutions in the world, and the most advanced nation in the world at the time, though tearing itself apart. And then in some sense, a life that's very different when they came to the United States, eventually to Peoria, Illinois, which I'll tell you more about in a second. But it was a very quiet life, a different life, a life sort of at the periphery in some sense. And so I was a little shocked by this. I didn't know this second part of Ernst Ising's life. And so I wanted to know more a little bit. And so, and this first sense of shock of a sense of why Peoria, why such a small place, is also the theme of this lecture, that in many ways, humans and the Isings in particular had very extreme different lives. But this is part of what it is to be human. And one of the things I want to do is to show you, using methods of statistical mechanics, that this is true. Okay, so here's Peoria. I'm talking to you from Chicago, where the arrow is on top over here. I think you see it. And Peoria is about 300 miles away. It's a lovely little city on the Illinois River, but it's really something that was a quiet college town, an industrial town. Caterpillar, the industrial company, was there for a while. But it's a very normal life, and hopefully, as Maria just asked Reinhardt, it was a very happy life, but a very, very different life. A life in a small place with probably more routine activities, a life that was quiet and happy, and not a life of excitement and change. So how is it that humans do this? And how is it that somebody as brilliant as they were, Ernest and Johanna, could do this? Okay, so this will be sort of a question. It's a question that seems humanistic, but I'll show you that has a statistical mechanics answer. Okay, so the synopsis for what I want to tell you about today is, as you know, in 2 lectures. So we're starting now into the first lecture, but I'll start in earnest in a moment. But it's about, I'll start with some general consideration about statistical mechanics and society. As you probably know, actually, statistics was really invented for society, not for physics. And so this is somewhat interesting and will basically set us on an arc to which we'll be able to return. Then I'll show you how the statistics of society, and particularly of cities, have some specific characteristics that we had to discover empirically by doing a lot of phenomenology and by data. And this is facilitated also by the present moment, a moment in which we see the whole world urbanizing and we have data from many societies. So I'll show you empirically what this looks like. And I'll show you that this is very close and has many echoes in things we know about statistical mechanics, but it's also different. And this is where precisely we start finding a bridge from taking the statistical mechanics we know in physics to new places. And then this will basically be summarized into what I'll call a new quantitative understanding of cities. So I'll show you, I showed you in my first page, essentially my book. It's a book about urban science. It's sort of an introduction, tries to be a total overview with, but it's very much inspired by methods that are mathematical from different disciplines, but it's also inspired by empirical regularities that we see everywhere. So in this sense, we have a new understanding of cities and society, and that will be sort of the content of lecture 1. Lecture 2 will segue to using more of statistical methods to describe what we see in lecture 1. And you'll see that the most interesting part is that there's sort of a duality, a relationship between physical space, energy and momenta, positions and momenta, energies, in the usual sense of statistical mechanics, and the new space, a space that we're just starting to consider in statistical mechanics that has to do with learning and interactions. And so learning is where information comes into statistical mechanics. And this is why cities exist and societies exist more generally, why complex systems exist. And so this is a relatively new thing. And so lecture 2 will be about how some of these things come into statistical mechanics and what starts to happen. So what I'll show you is not, work in science we've never done. So what I'll show you are mostly simple models, but I'll show you there's a certain logic to how these systems are put together. And there's something that I'll call adiabatic environments, invariants that have to do with certain conservations that show up in complex systems that relate these two spaces and that derive sort of a generalized thermodynamics. So in doing all that, I'll be telling you a lot about also society, both from the point of view of individuals like Ernst and Johanna, but also at large, as you might do in statistical mechanics for averages. Okay, so here we go. So the first thing I want to do is to really celebrate this idea of that we've heard from Reinhardt already, and that I think we all know, that Ising really gave us a new way of thinking across several domains that are very important in not only physical systems, but all systems, and particularly complex systems. So on the one hand, these systems are physical. They have things that moving around, that have motion, that generate statistics. And, classical example may be a gas in a box, but also the spins in an Ising model. But these models, as we study them in physics, are, as I like to tell my students, dead, right? So dead is not good. I mean, it's interesting for physics, but in many ways, what we want to do is to really think of how systems like this can come to life. And many of the questions that are on the table right now at the forefront of research have to do with how the kind of statistics that we do in physics and the data that we can now obtain become part of information, and not only in terms of machine learning, which the slide shows, but also learning in societies and the things that follow. So the most important thing really here is to have ways of thinking that allow us to make inroads, usually simple models like the Ising model, that allows us to start thinking about these systems in a way that's systematic and falsifiable, that basically gives us scientific standards. And in that sense are a little bit in contrast, not in total contrast, but in some contrast to approaches from the social sciences that don't do that. They basically take the whole and all the variations. Okay, so I don't think I need to remind you, but I think this is very interesting that the introduction of statistics into physics really came, in the late 19th century. It really, the singular moment was when Maxwell did this and derived, as you know, the famous Maxwell-Boltzmann distribution of velocities in a gas. Here it is, here in yellow. This is described, for example, in this not very well cited paper in Nature. So you can see that you can be Maxwell and even publish in Nature and not get so many citations. I don't think this is an example, but it's kind of funny. But he says in this paper that basically he was being inspired by things that people were finding in the social sciences. So I'll just read it quickly. The data of the statistical method that he was applying to gases are the same as those applied to social science. It is the number of individuals, which is important, the important element, and the regularity of the results is proportional to the number of individuals. So there's a sense in which we're averaging, and when we have many individuals, we can start finding regularities. So in saying this, we're not saying anything that is particular to physics, right? And Maxwell, in particular, had read Quetelet in France, who was, studying many characteristics of human beings and of society, from crime to just physiology. And in this sense, the Gaussian curve, which is basically Maxwell-Boltzmann's distribution of gases, of velocities of gases, was precisely what's being used. So he basically lifted his method, one of the most important and singular results in physics, from social scientists, which is kind of funny, right? So there's an interesting journal paper about this written by Philip Ball, who's a science writer, as you know, which describes this whole arc of how statistics, the word statistics, as you know, comes from the German for state and a little bit on the diagonal from city. And so in some sense has to do with the study of societies, not the study of physical systems per se. But this paper traces a bit of that history, and it's very interesting to read if you want. But I think it's entitled The Physical Modeling of Society, and it's really written from the lens of how it is that people like me and many of us are using methods of physics to studying society. But I think, a title that we could also use is, if you allow me to change it, The Social Modeling of Physics. So in some sense, that's what Maxwell was doing. He was basically thinking of social methods with many particles, right, interacting, let's call that social, to study physics. So there's sort of a duality, sort of a relationship that goes back and forth here that's interesting and that is coming back to life in new ways. So that will be a theme of what I have to tell you about today. So I want to connect another few strands because this idea of studying cities is actually also an old theme in statistical mechanics. This is Leo Karanov, in your paper, Yuri, with Ising and Reinhardt and so on, that was cited before. You have a quote from him. So Leo Karanov, as you know, is one of the co-inventors of the renormalization group. He also, probably like Ising, missed the Nobel Prize by a whisker because he used sort of the wrong method. But in some sense, he said precisely what I was trying to express, that starting with Ising's result, a change occurred basically because we had a simple model that allows us to reason through statistical mechanics. So in statistical mechanics, we could still start to use these methods to describe behavior of many particles at once. But Leo Kadanoff actually came to the University of Chicago later, but he was also very interested in modeling cities. And this is typical of what happened. I'll tell you more about the story in the post-war, and particularly these years of the 70s to 50s to the 70s. I'll tell you more in a second, and why that was. But what he was doing and what people were doing at the time was not inspired by knowledge of the phenomenon. They're basically creating this idea, which are basically systems dynamics, of systems that have many loops and so on, that would describe how a city or some other system with many feedbacks would work. This is still a tradition in complex systems, but it's a tradition that has stayed relatively divorced from data. This, for example, informed world models for the Club of Rome and other things like this. But in many ways, the contact with statistical mechanics was not here. So, and even for Leo Kadanoff, though we had many conversations at the end of his life, he just died a couple of years ago, didn't end up coming this way and making the discoveries that I'll be telling you about. Okay, so let's first just have a bit of an overview about statistical mechanics and basically how it works and what its principles are. And then I'll start taking you slowly, step by step, to social systems and cities. So in many ways, we've come by trial and error, really, but reflection a posteriori, to understand why statistical mechanics actually works, or how it's constructed, if you will. Uh, the sense that there is motion, that there's basically something in time that's creating variation, is essentially the most important part of the problem. It's this motion and the variations that creates that once averaged over creates statistics, usually stationary statistics, but there are some exceptions that I'll mention as I go. It's very important in general, though again, there are exceptions, that the interactions between the things interacting, like the spins in an Ising model or the particles in a gas, are local. For systems that have long-range interactions like gravity or naked electromagnetism, basically the energy diverges and you don't have something that, in some sense, preserves motion. You might have collapse or some change of state that then creates local interactions like in electromagnetism. And motion is bounded in phase space. So it means that in some sense, what's interesting is that, the gas is in a box. And so there's a force that contains it in a box, or in the Ising magnet, the sites are fixed, but the spins can flip, right? So in that sense, the motion is bounded and has a number of states, both in momentum and position or in configuration space, that can sometimes be enumerated, usually can be enumerated, and for which we can do combinatorics and statistics. And so the idea is that all of this makes creating a probability distribution that's stationary for physical states possible. Then basically where this probability is concentrated is around essentially surfaces that come from conservation laws, chiefly energy, and sometimes other conservations like particle number and others. And these basically dominate the statistics at large numbers. So this is basically the key to traditional statistical mechanics, but it's actually quite hard to describe what this energy would be in complex systems or in social systems, particularly because these systems become dissipative and driven. And so the procedure basically is that you end up writing some probability function, which is often based on some function of energy. This is basically what Ising did and what Pauli did, as you were seeing in Reinhardt's talk. Then you define some volume of phase space, or equivalently a partition function. This was the Z, the Zustandssumme that basically Ising was using for some of the first times when he was writing his thesis. And then this is basically already something that sums over states, and derivatives of this quantity gives you thermodynamics, things like pressure, temperature, and so on, which are nothing else than aggregate statistical averages. And sometimes as we change these averages, or we change something external, you get a change of state to phase transition. So it's kind of a little bit tragic, I think, interesting but tragic, that, as was mentioned too by Reinhardt, Ising actually ended up with a system that he could solve only in one dimension, and that didn't have a phase transition. So in some sense, his big result was a negative result. It was a method, but he didn't find the Curie point that was known experimentally. And I wonder how much of that had to do with him leaving research and going more into teaching. Okay, so with that saying, I want to introduce the city, and I want to start giving you a sense of why it is that sometimes, if we use a bit of finesse and good judgment, we can start creating averages that are meaningful and they're not just violence to the nature of people. So I'll return to this point, but let me just introduce the city in a moment. What I'm going to do is to show you a time-lapse video of New York City. I like these videos. People do them all the time. Sometimes they do them as sort of a tourist kind of attraction thing for people to come and visit the city. And what I want to, as I show it to you, I want to introduce two questions. The first question is that I want you to think about the cycles of the city, the fact that they have certain periodicity, particularly over the daily cycle, day and night, and then repeat with variation. And the second one I want to ask you is how many professions, so different jobs, are there in New York City? Okay, so let me show you the video. I won't show you the whole thing because it's a little long, but this will give you a sense. All right, so I think that's enough. These videos always makes me smile because they take you away from our daily perspective, even from an airplane or something. They speed up obviously time and they give us sort of different perspectives in space, particularly this sort of the statistical mechanics perspective of seeing it from above and imagining all these people and cars and everything in some sense in motion. So it's a bit like the gas, the gas in a box. Forgive me, it's not exactly, but you get the sense. And so in that sense, they give us, perhaps the hope or the misplaced feeling that we can start averaging and getting a sense of this system. But notice a few things. On the one hand, it's a bound system. It's finite in space, and also doesn't have infinite speeds and energies, right? Everything is moving, and moving quite fast, but it is in some sense bounded. Okay, has many agents. So a city like New York has about 20 million people in the great New York area, but that's about the size of largest cities, so 10 to the 7. But there's also a sense that as you look at, there are some images of the same intersection, day and night, that what's going on is basically has rhythms, but it's repeating itself with some statistics. And so it's that perspective, which is not quite right in the long run, but it's okay in the short run, that will allow us to start writing something that has averages that make sense and that will allow us to study the city. So that perspective is actually something that we'll use, but also that I will show you when it fails and what happens when it fails, which is very, very interesting because then we have sort of the growth and development of societies, which is another problem. Okay, so when we look at cities, just to summarize in this slide, what we may be able to model that gives us a statistical mechanics. On the one hand, we have many agents. So small cities, let's say, have hundreds of people, but big cities have 10 to the 7, probably not 10 to the 8. And we don't know if this is big enough, but it's certainly a system with many particles, if you will. Has the cyclical daily motion with variation, right? So this is kind of the basis for a lot of what we may be able to average. They're bounded in area and population. They have local interactions. I don't think I need to explain that. But what's really hard, right, is that if we zoomed in any one of us, we start having that people would have free will or agency, right? And even if we're not talking about people, sometimes in other complex systems, there's sort of a certain ability to adapt and have agency in complex systems. So this is pretty hard because it's something that at face value would start breaking a lot of the things that we assume in statistical mechanics. And then the other thing that is still statistical but different is that, and you saw this in this video, and you can see yourself as you go out after this talk, is that cities have enormous heterogeneity. Everyone is different. All the buildings are different. All the trees are different. So this is typical of complex systems. And then we also have global structures, things like institutions and infrastructure. Okay. So there's a question about how we may be able to bypass or use statistical mechanics given sort of these things that are, in some sense, warnings against the possibility of doing that. So at this point, we just don't know if we can do it or not. And so I need to jump to phenomenology, to basically what do we know empirically about cities? Can we identify any stable statistics? And the answer is yes. So what I'm about to show you is work that in some sense started at the time. This is a paper from 1947. So you see it's exactly when the Zips came to the United States, 47, 48. And this is work that happened after the Second World War because part of the war effort, particularly here in the United States, led to a lot of data collections and statistics in the sense of state. And people like Zipf, who is a linguist, started looking at regularities in society. So what you're seeing here is basically fares that people are paying in highways versus essentially population at the point of origin and point of destination divided by distance. And this is in a log-log scale. This is eventually known as the gravity law of movement. It's a curious thing that I can explain to you later, but I won't spend much time on. But people started finding relationships like this, which are essentially scaling relationships. As you can see, you pay more money in a way that basically is follows with this variable. And here's another one, also by Zipf, and this one became more famous. It's called Zipf's law, and applied both in linguistics, curiously, but also for the relative size distribution of cities. This is maybe one of the most famous laws of complex systems. The way I'm showing you is the way he wrote it in his book. His book was misguided from the point of view of theory, but empirically very interesting, and that's what we remember. But what you see here is the rank size rule. It's the population versus the rank of cities in the United States from 1790 to, when he was writing, it was mid-20th century. So what you see here are that these lines have approximately and only approximately the same slope. I put some of these gray lines here to show you that's not always true. But this means that the probability of a city of a certain size, little n, is basically 1 over 1 over 1 plus z. And z would be the slope that we see here. And this slope is approximately 1. It's not quite 1, and it's not quite a perfect slope. But basically, if it were 1, there's a very interesting characteristic that happens that I can basically compute the population in any size bin, taking the distribution, so the expected value of n, but in a range. And when I do that, I basically just get the log of the upper range over the smaller range. And let's say this is a factor of 2 or something. If this factor is constant, I have the same population in basically small cities and large cities. So one large city and many small cities that I can aggregate in this way by basically sliding the size of cities have the same population. So this is kind of a weird way of deriving something basically saying that there's no preference, according to Zipf's law, for large or for small cities. That a collection of small cities has the same total population as one large city. And this is true also of mid-sized cities and so on. It's a scale invariant distribution. And this is very puzzling, right? Because we can think about advantages and disadvantages of small and large cities. Think of Zipf himself, that when he lived in Hamburg, basically he was exposed to the whole, all that the world had to offer, which at the time was somewhat negative, right, for him in particular. But in Peoria, he has access to something quite different. Okay, so the other thing that people started discovering starting in the 1970s was this kind of thing that when you look for regularities in cities, you find things like this. So this is a paper by a labor economist that was studying at economic productivity. This is actually the profits of companies. And what we found is that if you compare the total industry in two different cities, when a city doubles in size, so you can compare, a larger city to a smaller city, its economic productivity per capita, per person, increases by about 15%. Okay, so this is kind of an interesting thing. So basically, in a larger city, per person, you can make more money by this multiplier. This will turn out to be an interesting number. And this is a paper written a little bit later by two economists who were interested in also behavior. So this is about violent crime. This is all American cities, but it's true of every other urban system we've studied. When a city doubles in size, again, you're comparing a larger city like New York to a city that's half its size, so maybe a city like Chicago or something, the per capita violent crime rate increases by about 16%. So numbers like this, 15, 16, 17%, sometimes 12%, are numbers that keep popping up when you do this. But notice what is happening here. What is happening is that it doesn't, whatever it is that we're studying, whether it's economic productivity or crime or whatever, is not really increasing in a way that's a lump, a certain fixed quantity. It's a percent. So it's basically a relative change in that sense. And this kind of change is called by economists an elasticity, and by physicists it's called, of course, scaling. it means that a percent change in one quantity begets a percent change in another quantity. And when this increases, when you get what I'm showing you in these two slides, which is basically that there's an increase per capita, economists tend to call this increasing returns to scale. So it means that you're getting more per person the larger the city than in a smaller place, which is quite extraordinary, right? Think about this. So this is at the source of many interesting properties of human societies, and as I'll show you, essentially brings us to the present moment in interesting ways. Okay, so when we looked at this, this is sort of, it's a blurry slide, I apologize for that, but it was the first scaling plot of this kind that we did. It was done by Jose Lobo, who's now at Arizona State University, and he's an economist, so he had access to wages. So what you're seeing here are wages in American cities versus population. It's in log, so that's why it gives us a straight line. I get to the math in a moment. And the slope here is 1.12, and this 0.12 is equivalent to this 15% or 16%, except here is 12%. Okay, but this is very interesting. It tells you that in a larger city in the United States, you make more money, your wage is higher, but obviously you also spend more money. And so there's sort of this acceleration of money circulation. And this tells you also that things like GDP of a city, which is nothing else than total consumption and total production, so it's approximately given by total wages plus profits, increase in a way that large cities have great advantages, at least from this perspective of economics, which is something that a lot of people care about. So this means, for example, that the economy of Tokyo, which is still the largest city in the world, is, when we did this, was a long time ago, comparable to the economy of Brazil, and at the time was bigger than the economy of India. I don't think this is true anymore. But the other thing is also true, is that the GDP of New York City was at the time 0.9 trillion, and it was comparable to Russia, right? So this is why, in some sense, Russia will lose the war, is that in many ways, economies that are based on cities and free exchange of ideas and so on, create these monsters of innovation and productivity that effectively end up being effectively the future of both innovation, economic performance, and so on. So this is kind of very interesting. So let me just take you through the math. So what I was showing you, those plots, is essentially a very simple relationship, like a scaling relationship like this that you see. So y is equal to some prefactor, y0, and to the exponent beta. This exponent beta is measured by data. And so when I go to log plot, which is what I'm showing, I was showing log of y versus log of n. I basically have an intercept, which is not the leg of y0, and I have a slope. So that's what I was showing you here, right? There's an intercept, which I'm not showing you, and there's a slope. And more carefully, what these relationships actually are is that you have to take them at the same time, cross-sectionally, and you get something like this, and that these deviations here are basically the scatter that you see around this line, and they're approximately Gaussian, interestingly enough, which means that the original quantity is log normal. Okay, so this is also interesting and consequential, that it will not be the theme for today. So when you put all this together, what you find is something like this, which tells you that urban systems, complex as they are, have very simple statistical characteristics. So I'm showing you here on the left in A is basically the wages in American cities, so similar to what I showed you before, but now over time. So basically it's going up in time from green to sort of this brownish color. So you see here in New York over time, and you see that mostly what's happening is that wages are going up and population is growing a little bit. It's moving also to the right. This is kind of the center of the cloud. And so you can collapse all this basically on the same point, which takes away growth, which is here in yellow. So you see that over 50 years, which this data covers, now about 60 years, almost nothing happens, right? It's the same relationship. So there's total data collapse, except that there's this growth that it took away, right? And then if you actually focus on these deviations from the line, you get that these deviations are not quite normal for wages for reasons that are interesting, but they're approximately normal. And that these deviations actually are not fluctuations as in physics, but they're actually adaptations. They're actually things that speak to the character of each city. So for example, Silicon Valley is rich, and some of these other places like McAllen, which is in the border with Texas, is poor. So this tells you basically that from this statistical perspective, things are very, very simple. There's a scaling law with an exponent. The intercepts are growing. So there's two quantities, and then there's the statistics of the deviations that's basically characterized by a variance and nothing else. Three parameters. Okay, so let me show you a few more of these. This is violent crime, I already showed you. This is for European cities, labor productivity. The number is about 1 + 1 = 6. It starts emerging, but this is kind of a meaningful number, as I'll show you. And so what I'm about to tell you about now is basically how to use scaling. And scaling is basically what statistical mechanics are for. It's to derive basically relationships like this that tend to be more general than even equilibrium systems. Okay, so many examples, the gas in a box, right? Very simple. So this is the basics of statistical mechanics. But in this case, at least for non-interacting particles, you just have that the energy is proportional to the energy per particle times the number of particles. So it's a very simple scaling law. It's linear because the system is free, and that the area is basically proportional also to the total population, the number of particles times the density. So nothing much happens. Everything is local, but still has interesting characteristics that allow us to build engines and so on. Okay, so for something a little bit different, but very familiar, if you think about diffusion, right, an experiment that you can do with your coffee that I did this morning, you drop a drop of ink or a drop of milk in your coffee, and you see it diffuse until it spreads, until your coffee gets a little bit brown instead of black, right? So what we study here is basically the spread of the cloud of milk. And we know that under diffusion, you basically know that the square displacement goes like time, right? And so here you get a scaling law that's a little different, that the average square displacement, or the displacement goes like t to the 1/2. And we could have created a statistical mechanics with a partition function based on what we know is the probability of diffusion. And we could have thought of this as a temperature, which is now a temperature that depends on time, for example. So this is just to show you that the machinery that we use in statistical mechanics is not just for equilibrium. There are ways in which you can use it to derive thermodynamic quantities and partition functions and so on that also apply to non-equilibrium problems. Another examples, a few examples of scaling relations, for example, this one, that the mass luminosity relation for a star is actually superlinear. So the reason I'm showing you this is that cities have a little bit of a relationship with stars in this sense, that what they produce, in this case for stars, light, is basically a superlinear function, a function with an exponent larger than 1, you see here, of their mass. And this is because the interacting reactors, so the products are really the result of interactions between particles that form the mass. And those interactions naturally give you exponents that are larger than 1. Okay, so essentially what these scaling relations tell you is that you have scaling invariance. That's what power laws do. But scaling invariance, which is basically given, is an invariance, a symmetry, and the dilations, as I show here. I'm not going to belabor a little bit the point, but this just shows that the kind of scaling law that I'm using is a solution of this kind of transformation. This just says that there's no particular size to a system that has scaling laws. So that system can occur at many different scales. And so a bit like Zipf's distribution of city sizes, this is saying that there's no particular size to cities so long as they obey this kind of relationship. So you can have a small city and you can have a large city. We saw from Zipf's law that approximately people don't have much of a preference. You find as many people in small cities and in a large city with the same population. But somehow this is something that we need to explain. Okay? Okay, so this is where sort of my work starts to come in. So I'm just going to take you through this now, and I'll go a little faster, but starts speaking to the properties that are specific to cities. So when you do a lot of these scaling analysis of data, what you start finding is that there are different kinds of quantities. There are quantities, for example, like I'm showing you here in blue on the left, which are basically the volume of roads, so the area of total roads, right? And what you see here is that this is what we call sublinear. The exponent, the slope, is less than 1. And then we have quantities like what I showed you before, GDP or wages or crime. They are superlinear, so they increase faster than population, okay? So this is what is often called increasing returns to scale and economies of scale. And what's interesting when you do a lot of this, that we observed in some of our first papers, is that maybe there's not two things happening, but there's only one thing. Because the number by which this exponent and this exponent varies away from one is about the same number. So there's a certain duality between space and essentially what is producing these social outputs. Okay? And the simplest case in which this happens, and the simplest case in which we get superlinear laws, have to do with basically with networks. So now instead of having something that's on the lattice with a fixed amount of connectivity, we actually imagine a system like, for example, the friendships between us, where you can connect to everyone in principle. And so in that case, you can connect to n people, and the total number of connections is that times n. And so you end up basically with scaling that goes like n squared. So the logic here is going to be that these superlinear exponents are essentially variants of this very simple phenomenon that basically have to do with how people are organized and move through space. So this is called Markov's law. It's the simplest one. And this is actually characteristic of systems that have no space, like the internet and some social networks. People have shown that, but it was actually invented for the early precursors of the internet, again, for that same reason, where people were trying to derive what's the value of telecommunication companies and their connectivity. Okay, so let me show you a model of where all this comes together. This is a model that I call, in the spirit, again, of Ising, of creating very simple models that I call the amorphous settlement, right? So the idea here is that these are houses. These are actually a map of a small Aztec rural village. So it's not a big city, and it's not a city with infrastructure. But these are houses, and the question you may ask is, why are they organized this way? And if you're a physicist, right, what you're going to ask is not so much the structure, the fine structure, but just how big, how dense this is, right? So you can characterize this by a radius, which basically tells you the characteristic length. And then you can ask, why aren't they more concentrated, or why aren't they more spread out, right? And so the answer essentially is that, or you can build an answer where you trade off essentially costs of movement with benefits of interactions. So when you move through a medium like this, you basically will move a characteristic length scale, which is the radius. So we're going to say that there's a cost that's proportional to that radius, and that's the square root of the area. And there's a benefit, and this has to do with a little bit of physics of scattering, that has to do with the number of people that you're likely to encounter. This has to do with the density times some number. So it's like a cross section times essentially the number density. So that's the benefit, just geometrically has to work like that. And what you find is precisely the kind of thing that we find in urban scaling, that the area of the city, in this case is the total area, it's not the roads, goes essentially like a sublinear exponent, which is 2/3. This just follows here from a and a 1/3. It would give you a to the 3/2, and then it's inverted. So basically that gives, the 2/3. And then essentially the product of interactions is n times n divided by a. So it's basically the number of people times what I showed you are the product of interactions, which goes like 4/3. Okay. So this is the essence of it, is basically a system that's bound, that's interacting, and that essentially creates more interactions per unit time as it densifies. So it's kind of a slow implosion of a sort, but I'll show you in a moment that it doesn't just implode. But what we find through this exercise is an exponent that's wrong empirically. It's too big, right? The exponents was more like 0.15, 0.16. Okay, so what happens actually in a city is that space must become, this again, it's just, you find it empirically, space is organized essentially so that there are spaces of movement, a sort of a network of infrastructure that allows you to move around and for the entire space not to be taken up by houses and built environment. And this, by the way, is something that doesn't happen immediately. It happens as settlement gets organized. So for example, it doesn't happen in informal settlements, so slums, and we have a lot of work about that. But this is a map of Chicago that shows the block structure, which is actually universal, though not necessarily on a grid. And so when you do this, the area of the network is observed empirically to basically go like the density, so a characteristic length scale, which is given by the density that I showed you before, times the number of people. So there's a little bit of infrastructure for each person that's density dependent. And so this gives you a number like 5/6. So the number away from 1 is now 1/6. So this can then be computed more seriously. In the interest of time, I'm not going to show you all this. It's in the book and so on. But this can be computed by essentially a model of the infrastructure of a city as a hierarchical network from local streets to highways with large flows. So this is the way in which you teleport through a city effectively. But when you do this, you start understanding essentially that the network of a city mediates this process that I just gave you sort of in mean field. And you can compute the length of the infrastructure and the area of the infrastructures through these layers through a geometric series sum. Sorry that I'm going a little faster through this, but this shows you that the length is area filling in the sense before. This exponent is 2/3, but the area of the network, which is actually the way the space is filled and ends up in buildings, is basically 1 minus 1/6. So this is kind of working a lot harder to get this exponent right. And so the fact that the city's network becomes important. This is, for example, what you find for Japan, which is true to what we expect. And then, very much like in physics, you can compute the cost of running currents over this network. And again, it takes a sum a little bit like before. And a resistance that has to do with that in a city, actually, you can take parallel paths. So it's a parallel resistor of a sort. And this gives you that the total energy dissipation of everyone moving around in the city scales superlinearly, like 1 plus delta. And so the energy dissipation per capita just has this delta. And remember, delta is 1/6. So this starts to get essentially the right numbers. And then just to finish this picture with social interactions, what you do is put people back in this infrastructure and look at the kind of interactions they can have. So the idea, again, is there are fast and slow degrees of freedom. The social infrastructure is a slow degree of freedom. People moving around, as this picture shows, are the fast degrees of freedom. We saw this also in the video. And so when you do this, you put somebody's relationships, which is an abstraction, a network here, you have to put it back into space. So that looks a little bit like this. So here's a person. This is what we call her life path. Okay, so she goes around every day and she comes back home and has a number of interactions. And at these interactions, many things are exchanged. Okay, and in a large city, what happens is that basically this infrastructure, the house gets smaller, the infrastructure gets bigger. This I could have shown you with the scalings I was showing you, but it means that the space is denser with more people. There are more interactions, more things to do with the same length of a path. So basically all the exchanges accelerate. And so you get something that's an accelerated social life. And this means basically that everything that's a social output, you get more per unit time. Okay, so this is the way you calculate it. It's basically the Druid model of scattering in a medium. And it has to do basically, again, with the probability of interaction, which I used also in the simple model. There's a cross section. You basically derive some kernel for when people interact and so on. This is all in mean field, so I'm not doing statistics yet. And this gives you that on average, the interactions go like a factor that includes a cross section, the strength of interaction. I put in this G, and then essentially the density in the relevant space. And this goes like n to the delta, again, as before. Okay? And so this allows you to just get a lot of different scaling laws, again, all in mean field, like land area, network volume, as you said, network length, average network width, if you want, or width of roads and pipes, interactions per capita, socioeconomic rates, power dissipation, land value, which is an accumulation of a few things, and then indirectly, things like the building heights, congestion, air quality as a result of, for example, power dissipation, and a bunch of other things. And so this has been verified all over the world, where we find, mostly agreement and a few interesting exceptions that then are studied in detail. So I'm not going to do that much, but I want to show you this, which is essentially that when you combine several things, for example, this parameter G, which is the strength of interactions, includes the cross section over the path, the daily path, but also the strength of interactions can be measured this way, which is the total, if you will, the GDP or wages divided by person, so per person, and the area per person is just a number that, according to the scalings I showed you, does not depend on n. It's an invariant. It's the same thing for cities that are big and cities that are small. But remember that each one of these quantities in the brackets is going in different directions. So what's happening here is that you're trading off more social interactions in a large city, so more social space, for less physical space in a large city, or vice versa, more physical space in a small city and small social space in a small city. But in some sense, there's an invariance that's suggested by the data and these scalings that allows you to think that people don't really have a preference in this trade-off, at least people on average, and that essentially the system has an invariance. And this will be the basis of what I'll show you in lecture 2. Okay, so I just want to finish. I'm more or less on getting to time, but I want to show you this part before I break, if I may. Then we can break a little longer, which is that this also changes people, because now you're interacting with more people that are more diverse. And so the way to see this, one way to see this is through the occupations, the jobs that people do. Okay, so here's basically, there's sort of this is measured by several statistical agencies. So some examples again for the US. And so these are given at different levels of resolution. So you can measure something very simple, which is the number of professions, which I'm showing you here in this plot, versus the total employment or total population on the x-axis. And what you see is that this can be measured at different resolutions, but as you increase the resolution, you see more and more professions. This is what you get from getting from red to blue. And so the question is, what is this scaling law for a number of different professions? And can we eliminate this saturating effect? So this is why we can start asking, how many occupations are there in New York City? The question I had asked you. And if you were to trust the saturated data, you get 630 occupations for New York. But you see that if you thought that this was not saturating, you'd have a lot more. So you can use something called, like finite size scaling in physics. I'm not going to go through this to basically derive that there is a scaling law in the infinite limit of resolution. You can test this within the sample, and this agrees with data. And this also gives you effectively that there's a universal distribution of occupations and so on that you can derive, which is very interesting. So each city, as it gets bigger, gets more occupations. And so there's this regime again, and another invariance, that as people get more connected, they get more specialized. There are fewer occupations per person. And so as that happens, there's sort of an invariant also. So people get more specialized and they interact more. So people change in this sense. Okay, so and so what this does is provide a model that existed since Adam Smith for what economic development is, or what social development is. Basically, you go from disconnected societies where everyone does more or less the same thing to rich societies with lots of information and capabilities where people specialize, but now they must interact. So they must create places where they can interact. So I'll elaborate this later. But this, I just want to leave it here. This sets off a massive instability. Like I'm talking like a physicist, okay? But you know what this instability is. What this does is that basically there's a connected phase, which we're taking for cities or urban systems of cities. And there's, if you will, to want to imagine a disconnected phase where people don't do this or do this very incipiently. And what happens is that when people are connected, they must specialize, they must adapt to what's around them. And this sets up a learning mechanism where people can spend more time per function. So they become good physicists or good lecturers, right, for example. And so it's this learning that basically leads to new functions in society and leads also to evolution in biology. And that sets up not only a structural instability to form cities, but also a dynamical instability that leads to growth. Okay, so this is what it looks like for humans. This is the growth of population since the first cities, and it's often called also the Great Acceleration. So I'll leave it there and break. I'm sorry, I went 3 minutes over. And then I'll try to explain what all that was in terms of statistical mechanical models. They're simple. I already gave you a sense, but I'll give you statistical mechanics more specifically.
All right, thank you very, very much for this talk, and we send you a virtual applause, although we can't do it in person. Let's open the floor for questions. I already see a hand raised by Yuri, so please go ahead.
Yeah, thank you very much for your talk. You spoke about sublinear scaling and superlinear scaling. Superlinear scaling with respect to socio-economical factors, and sublinear scaling with respect to factors which make cities similar to some biological entity, as an animal, right? And as I remember from papers of yours and of your group, finally you arrived to the conclusion that this will lead to the collapse, and to get rid of this collapse, you need innovation, right? And that's so in a way, the birth of the city already gives the date when the city will die. But in the course of evolution, there should be innovation which makes the new birthday for the city, so to say. Are you going to comment on this in your second lecture? If not, could you please comment now?
Sure, that was our first paper. Came out in 2007, but it was really work
Right.
like the plot I showed you from 2005, 2006. Yeah, that was our first attempt where we put it all together. And I think while we still stand by some of those things, I think the picture has been very much updated. So a couple of things from what you said. So, some of us, like Jeff West, of course, very instrumental in this. He was coming from biological scaling and creating models of vascular systems and so on that try to explain particularly how biological organisms use energy, so metabolism, and which is sublinear. It's a different sublinearity, and what we learned in doing this is that even the vascular system as a network, as sort of an infrastructure network, if you will, is different from what we have in cities. The difference is curious. It's hard to see from the eye. It has more to do with how it works. So in the vascular system, it's a centralized network, as we say, network. So it's basically the blood goes through the heart, right, and the lungs. So there's basically, so in a city, though, let's go with New York City, you don't go through Times Square or whatever the center would be to go from A to B, right? It's a decentralized network. You go locally. And so this has different properties, actually. So one is a system that's centralized, that delivers energy per unit time at the same rate to everybody. And the units are more or less homogeneous because they have the same genome. In a city is the opposite, actually. What you have is that motion is mostly local. The agents interact with each other and they're very heterogeneous. So one system actually slows down because of economies of scale, and the other system speeds up because effectively all the variety of interactions becomes available through this. So the systems are actually, in a way, interesting to compare, but upside down from each other. Now, in a city, what happens now to this idea of adaptation and collapse? So what's happening, what I was emphasizing so far, is that people individually need to adapt to each other because now they live in environments that are full of functions that others have, right? So I'll show you more mathematically how this works in lecture 2. But you have to find your niche. And this usually means that you have to do something very well, but it can be very specialized. So you can do quantum field theory or something, right? If you like. But we have to do it well if you're going to do it. So in a city, you find things like this. But what we didn't understand then in that paper, and what we still don't understand because it's in some sense the mother of all problems, the reason what I finished this first lecture with, is how this sets up dynamical instabilities in time. So I think what we said in 2007 is true, that this can lead to instabilities that rise very quickly and that lead to very fast growth, and that this growth is somehow not sustainable, but we don't know how. So we just said that this would not be able to go on in the first lecture, in that first paper. But since we've studied a lot of this, and so you need essentially adaptations in the system. These adaptations can be partly bottom up, new technologies, new ways of organizing production, new infrastructure that reorganizes mobility and so on. And that's what we see in that plot in 2007, is that there are reorganizations of New York City that allow you to continue. But these are somehow endogenous to the system too. So this system of the temporal instability, I'll touch on it on the second lecture, but in some sense it's the greatest mystery of all. It's essentially how do we continue to have economic growth and socioeconomic development in societies, and how this is connected to the dynamics we're discussing here, but how also much of it happens in time.
Thank you.
Thank you. There is a question in the chat that I will read. And if Yaroslav wants to, comment on this, we can do it together. The question is, how does it work with the simple city model? The benefits increase with smaller size. The cost of roads decreases with smaller size. So why don't you get a maximum value at 0 size?
Yeah, so we need to exclude this, which I didn't know, right? So that's a very good observation. So at small size, I was careful to show you what happens, right? But essentially, what happens at very small size, we have other papers where we study, for example, small-scale societies. But there's essentially a transition to very small societies where people become self-sufficient and where interactions, at least interactions over a large scale, interactions persist in the family and immediate kin, but essentially they cease to be frequent with large scales with society. So essentially, there's a different regime at very low sizes. Another thing, so you can think that there's sort of a limiting case, which I was speaking a little bit about this autarky or isolated society where everyone has to be self-sufficient. There's also sort of a regime that we studied. This may or may not be interesting to you, but there's a paper that does that regime that has to do with hunter-gatherer society. So hunter-gatherers actually they don't have settlements. Mobile hunter-gatherers get together periodically, but they don't have anything that we'd call a city or a village. But they have something that they call camps. So there's sort of temporary camps that people return to. And these don't scale like cities. And the reason seems to be because there's a lot of short-term repulsion, you could call it as a physicist, that has to do with conflict. So there's something new that shows up at that scale. And that in some sense is resolved by cities by creating things like walls and laws and so on that people get along. But there's always a small scale repulsion that's there that allows the system to be stable.
Okay, thank you. And I see the thumbs up by Yaroslav. There's another question by Reinhard. Please go ahead.
Yeah, so you showed a lot of scaling laws. And if I think of a city, you showed that there are many aspects you can look at. And my question is there something in your statistical treatment as scaling laws? Is there a relation between different scales? And if there is a relation, how it is formulated? Is there a minimal number of scaling? You see, if I think of a usual phase transition, I have a free energy, I have temperature and field, and then I have a relation between the scaling laws. So that's a very naive aspect, but how is it in such complex systems?
No, but it's not naive at all. It's the best question. So I started to show you that, but maybe I wasn't very clear. So what happens actually, a city, super complicated, right? As you said, who could hope for anything simple? But you end up with basically one parameter, this delta, right? And this delta is telling you something about essentially the density of interactions, which is basically has to do with density of encounters. So it's this parameter. In this parameter, I showed you quickly, but it's made up of the dimensionality of space and the fractal dimension of how people move around. But it's basically a single number. This number essentially sets up two spaces that are talking to each other. So there's only effectively one scaling. One is the space of mobility and the space of the cost of that mobility. So basically, there's the space of the city, which becomes this network of infrastructure, on which there's densification. So there are more people per that space. There's an increase in density. And there's, as you'd expect in a physical system, an increase in the energy cost of moving through a denser and denser space. And this forms an invariant. When you multiply one by the other, and I'll show you later why it needs to be multiplied, is basically phase space. The two regions of phase space is very much like the physical space of molecules in the box, and essentially the kinetic energy, or therefore the space available for momenta. So, but I'll show you that in the second lecture. So basically that has an invariance relative to size. So you can be in a place that has less density, but also fewer encounters, less cost. And you can be in a place that has more interactions, but also more cost, but more energy coming in. But there's this adiabatic invariance actually, because it will turn out that it has to do with entropy, a Boltzmann entropy. And then this appears again, and it appears more fundamentally, at the level of people. As you interact with more people, you can take a more specialized role and get from them their specialized roles. And so the space of connections, the number of connections versus your degree of specialization, which is a space, also have an invariance. So in a small place with few interactions, you're a jack of all trades, you do everything yourself. In a space with lots of interactions, you have a smaller space, internal, but more connections. And again, there's an invariance. So that's what I'm saying. This is a little idealized, but it's effectively the gist of what the averaging gives you a city is doing.
Thank you.
So I'm claiming it's actually very simple once you get to this, if you buy into the gist of very simple things.
Okay, thank you.
Yes, thank you. I don't see any more questions, so maybe we can take a couple minutes break, and in the meantime, we can set up for the next talk. And maybe I see you all in 5 minutes, right? At 20. Now it's 15.
20, okay.
Whatever your time is, it's 15, and we meet at 20, okay?